Okay, so hello and welcome back. This is part 2 of my nuclear astrophysics experiments deep underground at Lunar lectures. So I want to start off by showing you this picture. It goes back to an episode that happened in the Nuclei in the Cosmos conference, the first one in the series in 1990, when Fiorentini and Rolfs were discussing about a problem that had been bothering physicists for some time. As we all know, the sun has been shining at a constant rate for 5 billion years, converting 700 million tons of hydrogen into helium every second. This is quite staggering, and the way the sun accomplishes that is by fusing together protons, starting from the PP reaction producing deuterium. Here we see that one proton effectively undergoes beta decay by liberating a positron and a neutrino. The deuteron then fuses with another proton forming helium-3, and at this point there might be two possible outcomes, two different branches. 86% of time, helium-3 fuses with yet another helium-3, producing helium-4 and releasing two protons, and 14% of times helium-3 fuses with helium-4, producing beryllium-7 and liberating a gamma ray. At this point, beryllium-7 can either capture an electron, producing lithium-6 and a neutrino, lithium-7, and then lithium-7 captures another proton and eventually forms beryllium-8, which then immediately splits into two alpha particles, or 0.3% of times beryllium-7 can capture a proton forming boron-8, which then decays to beryllium-8, liberating a positron and a neutrino, and then again beryllium-8 decays into two alpha particles. So effectively, this sequence of reactions known as the PP chain converts typically 4 protons into one helium nucleus, and 2 of the protons are also converted into neutrons by undergoing beta plus decay. Now, of course, we have no way of knowing what happens in the sun except if we can directly detect the neutrinos coming from these various reactions. And indeed, some 30 odd years ago, people were thinking about this as a possibility of checking whether our understanding of the inner workings of the sun were accurate. And already in the 60s, Ray Davis had started his pioneering measurements of neutrinos coming from the sun using his detector, the Homestake mine. This is a picture from 1967 showing this huge detector in construction. Now, he was later awarded the Nobel Prize for his pioneering experiments, but the problem was that for about 30 years, all experiments, starting with his own, showed that we only were able to detect about 1/3 of the expected neutrino fluxes coming to Earth. And this was a bit puzzling, so this was dubbed as the solar neutrino problem, and people started looking at possible solutions, of course. One might have been perhaps wrong assumptions in the standard solar model, or possibly a poor understanding of the properties of neutrinos, or perhaps some unclear nuclear inputs. And in particular, people had started wondering whether if there was a resonance in this reaction, whether maybe this route could occur more often, and in so doing effectively switch off 2 of the 3 neutrinos expected from the sun. So of course this was a very interesting idea, but the problem was that a direct measurement of its cross-section was necessary, and it was necessary at the energies at which this reaction takes place in the sun. Now, if we go back at what we've seen in my previous lecture, we can express the yield of a reaction as the product, or indeed, more accurately, this should be the number of reactions, okay, as the number of particles in the beam, the number of particles in the target, the cross-section, and the detection efficiency. Now, if we put some standard numbers for typical stable beam experiments, we have typically beam intensities of the order of 100 microamps, and so this translates into 10 to the 14 particles per second if we assume singly ionized ions. For targets, we have typically of the order of 10 to the 19 atoms per square centimeters if we use solid-state targets. The cross-section is of course given by nature, we cannot change that, and let's say as a kind of characteristic order of magnitude, let's assume this is of the order of 10 to the minus 15 barns, bearing in mind that sometimes it could be even lower. And the detection efficiency, which can be in principle 100% if we are detecting charged particles, or 1 to 10% if we are detecting gamma rays. So if we put all of this together, we end up with a kind of number of events that we expect to detect between 0.3 and 30 counts per year. Now, even if you are on a 4-year PhD project, this is not fantastic stats, as you can see. So clearly there was a big problem as to how do we deal with these low cross sections, low yields, and therefore poor signal to noise ratios, because it is as if we wanted to hear a bird singing in a stadium where a goal has just been scored. So the idea here is we either improve the signal, but of course there is a limit to how much beam current we can use, because ultimately we may end up having problems in focusing the beams and making sure it stays within a kind of confined region of space, because of course charged particles will repel each other, or we may end up burning our targets if we put too much beam current on them. Of course, we can increase the number of target ions, so the atoms that we put on a target, but again, there is a limit to how thick we can make the target, because eventually, as the beam goes through the target, we have seen in the previous lecture, it loses energy, the cross-section goes down, and so, of course, the latest layers of the target do not contribute to the yield. We can increase the efficiency of our detection system, but we cannot go beyond 4 pi, which in general is also very hard to achieve. Another possibility is clearly to reduce the noise, i.e. the background, and we'll get back to that in a moment. So ideally, given that a lot of these measures have already been exhausted, one needs to have a combination of both. For example, reducing the noise may be through shielding our detection systems and making sure that we become insensitive to anything else but our reaction. So this was indeed what Fiorentini and Rolls were discussing, how do we improve the signal-to-noise ratio. And then it appears that Fiorentini suggested, why don't you do your measurements underground? I don't know what Rolls replied, but of course, knowing him, I guess he might have said, this is such a great idea, it could have been mine. So, and this is how eventually the Lunar laboratory came to be. This is because if we now step back and look at the sources of background, we see that the vast majority of the background comes from natural radioactivity. There is also a component of cosmic rays as well as neutrons from alpha and reactions and fission. And so, for example, if we were to plug in a germanium detector in here, even in our houses, okay, we would observe a characteristic spectrum very similar to the one shown here, where we would see lots and lots of counts up to about 3 MeV, and these are gamma rays associated to natural radioactivity. And then there would be a strong component that is effectively induced by cosmic rays and the interaction of cosmic rays with our detector, or possibly also neutron-induced gamma rays. So this means that if we want to reduce the background, especially the one produced by cosmic rays, it does make sense to go underground, and ideally in a location which is poor in radioactive elements such as uranium and thorium. And so the location was soon found. Indeed, back in the early 1980s, Antonio Zecchichi was convincing the Italian government to dig some big tunnels during the works to construct the motorway, from Rome, situated here in central Italy on the west coast, and Teramo on the east coast. So in the during the construction of the motorway, he suggested to dig some tunnels and to locate a laboratory for nuclear physics dedicated to rare event studies. So this is how the Laboratorio Nazionale del Gran Sasso was born, and as part of this, it was decided to install a small accelerator in one of the side tunnels of the laboratories. This accelerator is Lunar, Laboratory for Underground Nuclear Astrophysics. And the advantage of going underground becomes immediately visible. So this is the kind of same background spectrum that I showed a moment ago. If we go underground at Luna, this is the characteristic gamma ray background that we would observe. Clearly in this region that is dominated by cosmic ray interactions, we see that the background is really reduced by over 3 orders of magnitude. The reduction here is somewhat less, it's about a factor of 10, but by further shielding the detection system with, for example, lead bricks, it is possible to considerably reduce the background in this region as well, as shown here. So the first Lunar accelerator consisted in a small 50 kilovolt accelerator that was installed in 1992 and remained operational until 2001. The accelerator had essentially a duoplasmatron ion source mounted on a 50 kilovolt platform, an analyzing 90-degree magnet, and a target chamber. And this was entirely built by students. This is a picture of the actual setup, but now this detector has long been dismantled and it's been put in a history museum in Teramo. The first reaction that was studied indeed with this small accelerator was the helium-3, helium-3 2p reaction, because as I said, people were looking for a possible solution to the solar neutrino puzzle in case there was a resonance in this reaction. Now, these are the experimental data taken also elsewhere, of course, because Luna 50 could only go below 50 kV. And these are indeed the data points that were measured underground. And as you can see, for the first time, it was able to actually measure experimental data within the solar gamma peak for the first time. Sadly, no resonance was found, and so clearly this indicated that the solution to the solar neutrino problem had to be looked for elsewhere. I would like to point out that the lowest energy measured here, which has a huge error bar as you can see, had a cross-section of 20 femtobarns, corresponding to about 2 counts per month. So clearly there are huge error bars, and clearly it's extremely difficult to go any lower. But nevertheless, it was an outstanding measurement, and as I said, it excluded a nuclear solution to the missing neutrino problem, which was later solved, as we know, by the discovery of neutrino oscillations, which led to the Nobel Prize in Physics in 2015, given to Kajita and MacDonald. Indeed, based on this success, here is a letter written by Bacall, who was the father of the solar standard model. He said, I had the opportunity to see for the first time the results of the lunar measurements on the helium-3 helium-3 reaction. This was a thrill that I had never believed possible. These measurements signaled the most important advance in nuclear astrophysics in 3 decades. So clearly there was a major achievement, and based on that outcome, the collaboration was later able to acquire a bigger machine, which is still in use today. So this is our 400 kilovolt accelerator. For those of you who have never been at Luna, here is a little video clip. This is the tank. The machine fits into a very small room. Here we have the analyzing magnet, and at Luna we have 2 beam lines. One is used for solid state targets, and the other one is used for gas targets. So depending which reaction we want to study, we use one or the other beam line. So here you can see a BGO detector around the gas target, and this is the beam line for the solid state target. And this was for an experiment which required considerable lead shielding. So here we used a Germanium detector, and here I have another video clip that shows the germanium detector and the setup being opened. So normally during the measurement the germanium is pushed forward, very close geometry. So this is the backside of the target, which is constantly water cooled to avoid melting it under exposure to intense beam. So this is a kind of bird's eye view of the accelerator and the two beamlines. So Lunar has operated for about 30 years now, and as I said, it's led to some remarkable results. I've already mentioned the very first measurement, but the first measurement done with a 400 kilovolt machine was the nitrogen 14p gamma cross-section, which led to another major kind of result, which was to increase the age of the universe of globular clusters, and therefore by extension of the entire universe, by 1 billion years, and bringing these in better agreement with other independent estimates. Another measurement later on was magnesium 25p gamma, which placed stronger constraints on the amount of aluminum 26 that can be produced in some astrophysical sites, and these in turn has huge implications for the detection of the 1.8 MeV gamma ray line observed in the interstellar medium, which is associated to the decay of aluminum 26. Later on, a D-alpha reaction excluded a nuclear solution to the lithium problem, and another one on the oxygen 17p gamma placed firmer constraints on the amount of fluorine-18 that can be produced in nova. And some of you may be aware that fluorine-18 is a good indicator of nova explosions in principle, because it is a beta plus emitter, and so one can detect the 511 keV associated with nova explosions, even though at present, at least to my knowledge, there is no direct detection of these signature from fluorine-18. And then more recently, new resonances have been discovered in this sodium-23 with possible implications for the abundances or some isotopic anomalies in presolar grains. And in general, there have been many other reactions studied at Lunar, which has been operating, as I said, for almost 3 years now. Some of these reactions have led to the smallest, lowest cross-sections ever measured, and indeed they have helped us understanding in greater detail many of the processes listed here. Now, in the remaining of this lecture, however, I want to focus on some more recent studies, and specifically I've picked up 3 examples, one leading to gamma rays, one to charged particles, and one to neutrons, just to show you how an underground location can indeed be beneficial, not just if we study reactions that produce gamma rays, but also in the other cases as well. So let me start with the first of these examples. I'm sure you all know that the cosmic microwave background, or CMB radiation, is the oldest electromagnetic radiation that we can see still today. It goes back to about 380,000 years after the Big Bang. This was accidentally discovered by Penzias and Wilson in 1967, and it's been measured to exquisite precision by the Planck collaboration. Now, if we want to look at the universe a little before that, however, the only handle we have is Big Bang nucleosynthesis. And this really allows us to probe the state of the universe before this cosmic microwave background radiation that we can still detect today. So, because this is the time when the universe was dominated by radiation. So what is Big Bang nucleosynthesis? It's essentially a network of nuclear reactions. I've presented some 11 here, which are the most important ones. And the beauty of this BBN theory is that it allows us to predict the primordial abundances of light species, helium, deuterium, helium-3, lithium-7 as a function, essentially, of one parameter only, namely the baryon density of the universe, the density of ordinary matter. Of course, this is under the assumption that there are only 3 neutrino species, which is one of the key assumptions of the Standard Model. And given that this baryon density has been kind of pinpointed to a high degree of precision by Planck, it is now possible to say, okay, the abundance of these light elements must have been what is shown here by these circles. Now, of course, one can also invert the problem and say, if we start from the predictions of these abundances and compare with the observation values for each of those elements, we can find a common region shown here in blue that gives us an indication of what the baryon density should have been. So basically, using BBN, we can infer a value of the baryon density at the early epoch of the universe and compare it with the baryon density measured or inferred from CMB, from the cosmic microwave background. And of all the light elements, deuterium is an excellent baryometer. It's an excellent indicator of the value of the baryon density in the early universe. And this is because deuterium is only produced during the Big Bang, nucleosynthesis, and it's destroyed afterwards during stellar evolution. Deuterium abundance, as you can see from the slope of this red curve, is also the most sensitive to the values of the baryon density, which I've indicated here with this omega BH square. And it also depends on the effective number of neutrino species, NF. So clearly, if we focus our attention on the abundance of deuterium, primordial deuterium, we can try and figure out what the baryon density should be or would have been back then and compare it with CMB. I should also point out, however, that the baryon density inferred from BBN refers to the early epoch of the universe, whereas the baryon density inferred from CMB refers to the recombination epoch, so when the universe became opaque, if you like, to radiation, so when matter, nuclei and electrons started to recombine, which, as I said, happened about 380,000 years after the Big Bang. Now, the key thing here is that according to the Standard Model of cosmology, the so-called lambda CDM, the baryon density from the beginning can only have changed as a result of the expansion of the universe. And this is something that cosmologists can calculate. So if we compare the present day value of the baryon density inferred from BBN with the one inferred from CMB, and the two are the same, then this can provide evidence that the standard model of cosmology is indeed valid. Conversely, if the present value of the baryon density inferred from the BBN is different from the one inferred from CMB, then this may point towards the need for new physics beyond the standard model. So having two independent determinations can really provide very useful tests. Now, for this, as I said, we need to know the prediction based on BBN theory, but also astronomical observations of deuterium in particular. Now, astronomical observations of primordial deuterium abundance have now reached 30% accuracy, whereas BBN predictions of deuterium abundance were, before our measurement, still affected by large uncertainties. And these uncertainties were related in particular to this DP reaction that destroys deuterium and forms helium-3. So high precision data were required in the energy region relevant to Big Bang nucleosynthesis. And just to show you the status of the art before our measurement at Lunar, there were measurements done at very low energies. Indeed, this measurement by Casella et al. Was done at the Lunar 50 Kilovolt Accelerator in 2002, but this explored a region relevant mostly to the deuterium burning in the sun. For BBN energies, we're interested in a much higher energy region, and here the data were rather sparse. In fact, this green data appeared after our measurement was completed, although we hadn't quite published by then. but we had done our measurement at Luna. So when we started, only these blue data points by Ma and this single point by Griffith were available. We also had a kind of theoretical, or if you like, a best accepted value of the astrophysical S factor based on available data sets back then, done by Adelberger et al. In 2011. And there was a theoretical prediction by Marcucci in 2016, which however was at odds with the kind of best fit from Adelberger. So clearly there was quite some tension and better data were needed. So this is when we decided to study this reaction at Luna. And for this we use a setup shown in this picture, and this is a kind of cartoon. So basically we have a beam coming from the left. This is our gas target that contained deuterium, 99.99% isotopic purity, maintained at a pressure of 0.3 millibar, and a germanium detector that effectively was used to pick the gamma rays emitted by the reaction. We then had a calorimeter. This is a picture of it, so it's located at the end of the gas target, and this was used to stop the beam and to do a measurement of the beam current directly on the calorimeter. And just to give you an idea of the quality of the data, I'm showing here two spectra taken at the lowest beam energy and at the highest beam energy that we explored. And here you see in blue the measurement done with the deuterium gas in the target chamber, and in gray a measurement done with the helium gas, which obviously is inert and doesn't give rise to any reaction, so certainly it doesn't interfere with our DP. And as you can see, in the energy region of interest for the gamma rays emitted by our reaction, there is essentially no background. So this allowed us to extract values of the cross-section with a good degree of accuracy and precision, even at the lowest beam energy that we explored. At higher energies, again, repeating the same measurements with a different gas, we noticed that there was a significant contribution from a beam-induced background, specifically due to the interaction of the proton beam with any fluorine-19 contaminant present in the experimental setup. And this led to a significant amount of gamma rays, which of course affected the region of our measurement. But again, if you can look at the gamma rays from our reaction, these were still clearly visible, and we were able to subtract the beam-induced background and still obtain meaningful data with a good statistical precision. So in the end, we were able to measure after some 4 years. It was really an extenuating campaign. We were able to measure the cross-section of a broad energy region, in fact the entire energy region of interest for the BBN. And here I plot the results in the form of the S factor. And as you can see, the error bars are really very, very small. This is the most precise measurement of this reaction to date, and the overall error bars are always below 3%. These results were published in Nature, and we were able to perform now a best fit of all available data sets and find that this S factor is indeed a bit higher than the one assumed by Adelberger, even though it still remains lower than the theoretical calculation, so there is still some tension. But the important thing is that we were able to significantly reduce the uncertainty on this S factor with dramatic consequences for the cosmological implications. And in particular, I just want to focus your attention to our new value of the baryon density, which was, as you remember, our key goal. So in blue here, you see the value obtained by the Planck collaboration using CMB, and in red is the value, indeed the range of values obtained using our new predictions of deuterium abundances following the measurement that we did at Luna. And as you can see, the central value is now in much better agreement with the value by Planck, and also the uncertainty on this value is about a factor of 2 smaller than the uncertainty associated to previous determinations done before the most recent Luna data were available. So clearly these results were quite important and effectively confirmed that, at least for now, the standard cosmological model seems to be on safe grounds. The other case I want to present is that of some anomalies in the presolar grain compositions. Now, grains are small inclusions found in meteorites. Meteorites reach the Earth from outer space. Maybe the most famous example is the Aliotta meteorite. And as I said, very often there are some tiny inclusions that reveal isotopic abundances that are at odds with the values that we observe in general in our solar system. So this seems to indicate that the origin of these presolar grains is indeed presolar. So these grains must have been formed from stars that existed before our solar system was formed, and then somehow were included in material that is still in our solar system, and eventually some of these little meteorites can reach the Earth. Of these presolar grains, there are two broad categories: carbon-rich, diamond, graphite, silicon carbides, and they seem to be rather well understood, and oxygen-rich, which can be silicates, aluminum-rich, oxides, and so on. And in particular, among the oxygen-rich solar grains, there are two distinct groups. One is group 1, which is shown here, that displays an excess of oxygen 17, so you can see here, compared to solar values, and values of oxygen 18, which are kind of similar to solar. And these grains, or their origin, is well understood, and they are believed to come from red giants, typically with 1 to 3 solar masses. There is, however, another group, shown here, group 2, which makes up for about 10% of all these oxygen-rich grains, which display an excess of oxygen 17 and also a significant underabundance of oxygen 18. The origin of this is highly debated, or has been for some time, and as it turns out, a key reaction to understand the origin was the oxygen 17 p-alpha nitrogen 14 reaction. So this was the focus of the project of a PhD student of mine, Carlo Bruno, and we studied this reaction, and I just want to summarize very briefly the current status of it. So if we look at the kind of level scheme of the compound system, fluorine-18, we see that there are two levels, one at 70 keV and 193 proton beam, that can provide resonant contributions in the energy region of interest. However, most of the reaction rate is kind of governed by these 193, which here is given in center of mass energy, so 183. And there is this lower energy at 65 keV, which was still poorly known, but it was believed to be important at lower temperatures. And so this was a key goal of our measurement. We wanted to determine the resonance strength of this 70 keV state, but to do this we needed to study the p-alpha reaction and detect alpha particles with relatively low energy. So for this we devised a setup in Edinburgh. Here we have the beam impinging the target, and the target is surrounded by a dome that hosts large area silicon detectors. However, by having these detectors very close to target, and we also see lots of elastically scattered protons, and we needed to shield the detectors from them, otherwise we would kill the detectors in a matter of minutes. And so we had to place some aluminum foils, protective aluminum foils, before the detector. And this is a picture of the setup, but basically this means that after the alpha particles so let's say the reaction takes place in the target. So protons hits oxygen 17 in the target, and then alpha particles are emitted, and they go through these aluminum foils, which are placed here. And by the time they reach the detector, they will have significantly low energy. So this is, for those of you doing this kind of measurements, this is very challenging. And so that was rather tricky measurement. And one of the key things we did, first of all, was to assess the level of background, also because at such low energies, we really were very sensitive to all sorts of background contributions. So we did measurements both in Edinburgh and at Grand South, so using the scattering chamber I showed, both with and without lead shielding around it. And what we came up with was this comparative spectrum that shows 4 different background spectra. One in yellow is the one that we observe underground just by plugging in the setup and starting our measurement without any beam and without any shielding, nothing. So we obtain this yellow curve. If we shield our setup with lead, we obtain some improvement, especially in this lower energy. But when we go underground, we get even better background suppression, especially in the energy region around 200 keV, where we expected to see the alpha particles from our reaction. So indeed, we measured a factor of 15 reduction in background, which for this particular measurement was absolutely critical. And the way we proceeded was we first studied the 193 keV resonance, which is well known. We have a reference for its strength. And so with this measurement, we identified the region of interest where we expected to see our alpha particles. And then we did the measurement with a lower beam energy to investigate the 7 keV state. And indeed, this is what we obtained. We did measurements both off resonance, with beam and without beam, and on resonance, so around 70 keV in the lab. And you can see that there is a hint of an excess of counts in the energy region around 200 keV. And indeed, when we do a subtraction, we observe this signal with a statistical significance. So thanks to this measurement, we obtained the most accurate result to date on the resonance strength for this important reaction. This is, again, a spectrum that shows the level of background that we would have observed overground, and so clearly we would have never been able to observe this tiny little increment had we done the measurement overground. So this shows once again the potential and the impact of underground measurements. Based on the revised value of the strength, we were then able to revise the reaction rate, which turned out to be a factor 2 to 2.5 higher than previously assumed. And so these again led to significant consequences for the amount of for the origin of these pre-solar grains. And in particular, just to give you a little bit of background on the 2 possible scenarios that were envisaged, one could assume that these grains come from massive AGB stars, which operate under the condition of so-called hot bottom burning. So essentially, there is hydrogen burning taking place here. So for example, the oxygen 17P alpha reaction would take place here in this hydrogen burning region, and material from this region can then be brought to the surface of the star through convective motions. And this hot bottom burning takes place at relatively high temperatures between 60 and 100 million Kelvin, and can be responsible for the kind of ignition of this reaction we've been talking about. Another scenario that people had proposed was the cool bottom processing, where if we are now dealing with low mass AGB stars, the temperatures are quite a bit lower, and so there isn't enough depth in the convective layer to reach into the hydrogen burning region, so that one had to invoke ad hoc extra mixing processes, which however weren't very clear. So basically, before our measurement, the adopted rate was based on a work of Iliadis from previous oxygen-17 p-alpha measurement. And if you look here in pink at the values of oxygen-17 to 16 expected from these pre-solar grains, effectively these could have only been produced in low mass AGB stars, but not in high mass AGB stars. But the low mass AGB stars present this problem of having to invoke extra mixing processes that aren't quite clear. With our new rate, however, we can account for these values of abundances of oxygen-17 because our revised rate is such that it really intersects this region even for massive AGB stars. And so basically there is no need to invoke any extra mixing, and AGB stars, massive AGB stars, or rather maybe intermediate mass AGB stars, are now seen as the likely site of origin for these pre-solar grains. So this was quite a remarkable result, and it was published in Nature Astronomy. And basically we were able to show how, if we look back at the grains that we were interested in, previous rates cannot reproduce these abundances, they all remain too high. But with the new lunar rate, the same stellar models now lead to solar grains that can have the required abundances of oxygen-17 and 18. So this was again another important achievement. The final example I want to mention is related to the creation of heavy elements, elements beyond iron, because we have seen that light elements are produced during the Big Bang, elements up to iron are produced during stellar nucleosynthesis, typically quiescent burning, and for higher elements the key is either in the slow or the rapid neutron capture processes. The problem is that neutrons are unstable. Free neutrons decay in about 10 minutes, and so of course in order to make either the S or the R process, we really need to find sites where lots of neutrons can be produced. And specifically for the S process, the main source of neutrons is the carbon-13 alpha N reaction. Now this reaction again is important in AGB stars, because this is believed to be a very important site for the S process. The energy region of interest for this reaction is around 130 to 150 keV, and as you can see, there have been lots of measurements trying to pin down this cross-section, or indeed the S factor, but none of these so far had ever reached the energy region of astrophysical interest. And so instead we had to rely on extrapolations of higher energy data. However, as you can see, there are lots of discrepancies already at higher energies. There are data sets that differ by large amounts, and these discrepancies is not quite clear. And at lower energies, of course, error bars become considerable, so it's difficult to guide the extrapolations. And indeed, there are different ones depending on the models that people use. So this was an ideal case, once again, to study underground. And this was done at Lunar, and the spectrum shown here is the background of, the neutron background spectrum that you can observe overground or underground. These spectra were taken using standard helium-3 detector tubes. Helium-3 is a useful detection medium for neutrons, because helium-3 gas captures neutrons and produces charged particles, a proton and a tritium, and it is indeed the presence of these charged particles that can be detected fairly easily and reconnected to the presence of a neutron hitting the detector. Now, if we do the measurement above ground, so on any surface laboratories, this is the typical background spectrum that these helium-3 detectors would produce. Underground at Lunar, we were able to measure a considerably lower background, but still not low enough for our purposes for the carbon-13 alpha N reaction. And this is because aluminium, which is the material normally used to build these helium-3 detector tubes, so the container of the helium is aluminium. Aluminium is a dirty material, so it contains impurities, and even though these are at a lower level for most standard purposes, for our measurement this was still too high. So eventually we resorted to using purpose-made stainless steel counters containing helium-3, and with these counters we obtained a further reduction in background, and you can see here compared to what we measure on the surface is over a factor of 1,000 lower. So for the actual measurement we used both proton beams to check the status of the target, and also obviously for the measurement helium-4 beams at energies up to 400 keV. We used 18 of these stainless steel helium-3 counters maintained at a pressure of 10 bar, and we used two different configurations, one with the detectors mounted vertically with a vertical target holder which contained several targets so that we could replace the targets very easily without having to dismantle everything. And these measurements were done for detector commissioning studies and also to study the performance of the target under beam bombardment. And then for the actual measurement, especially low energies, we used a setup where these counters were mounted horizontally. The target was mounted here, so we embedded everything very close to the target, and we optimized the efficiency, detection efficiency, to increase the measured yield. Of course, we did extensive measurements and simulations to characterize the detectors in both configurations. We achieved efficiencies typically of 33 or 38%, depending on which configuration we were using. And ultimately, for our measurements, we also need to keep under close scrutiny the behavior of the carbon targets. So this is a characteristic thick target yield that we measured on the enriched carbon-13 targets at Atomki in Hungary, just to monitor the status of these targets and decide when it was the right time to change. So we did several tests, and eventually we noticed that after accumulating about 35 microcoulomb on target, we would observe a reduction in the amount of carbon-13 still present, and so a reduction in the yield of about 17%. So that clearly indicated that we had to replace targets. So targets were replaced frequently after 33 coulomb of beam accumulation on them, of charge accumulation. And so finally, we were then able to complete our measurements, and the results are shown here. These are our black dots, and as you can see, this is a huge improvement compared to the previous direct measurements shown here in green, those by Drotlev. And we were able to significantly reduce the uncertainties on these data points, but also to further lower the energy at which we carry the measurements. In fact, we basically enter the Gamow peak for the first time for this reaction. Now, these results have just been published, or rather, they've just been accepted on PRL. I hope they will come out very soon. And as preliminary consequences of these improved reaction rate measurement on the carbon-13 alpha N, we have run some nucleosynthesis calculations which show that some nuclei, or rather the abundance of some nuclear species, is varied significantly, with the most significant of all being that of iron 60, which is increased by about 100%, and is outside the scale here. So clearly another important measurement that adds to all the previous achievements by the collaboration. So there are, of course, a number of other studies that we have also carried out. I won't go in any great detail for this because I'm conscious of time. So another one was about a reaction, the neon-22 P gamma, which takes place in the neon-sodium cycle and is relevant for the so-called sodium-oxygen anticorrelation in globular cluster. And again, we were able to push measurements to a much lower energy than before, and therefore to reduce significantly the uncertainties on the reaction rate of this reaction. Another study, which again involved alpha particle detection, was the oxygen 18P alpha, which is important for nucleosynthesis and mixing processes in AGB stars. Again, our rate, which is shown in black here, is a bit more precise than previous ones. And as in the energy region of interest, we have something that is in pretty good agreement with previous values. But as I said, the uncertainties are reduced, which lead to reduced uncertainties on the amount of oxygen 18 which survives this reaction and can be produced in AGB stars. And finally, another study on the lithium-6 P gamma, which excluded the possible presence of a resonance, which had been advocated by a previous study by et al. In 2013. So again, these are the most recent examples, and I would like to finish off by looking ahead at what comes, hopefully, in the near future. I'm sure most of you are aware that the collaboration has been able to acquire yet another accelerator, Lunar Megavolt. This is a 3.5 single-ended machine which will able to produce and accelerate proton and alpha particles just like the other one, however with higher beam currents and also importantly over a broader energy range, so that this will give us the possibility to study reactions over an extended energy range and therefore aid extrapolations. But then, more importantly perhaps, this will also allow us to accelerate carbon beams, which is rather unique for underground laboratories. And with this, we plan to study a key reaction that I'll mention in a moment. So this is just a kind of layout. We have started, that the machine has now been transferred to the LNGS, and we hope to start commissioning at the end of the year and starting operations sometime next year. So there is a lot of activity going on at the moment. So with this new machine, as I said, we're going to use the nitrogen 14 P gamma as a commissioning reaction, but also this reaction will be very important to study again because of the tension with the solar metallicity in the solar core that I mentioned in my previous lecture. And the key study with carbon beams will be that of fusion between two carbon-12 nuclei, which is one of the most important reactions for massive star and their evolution. And then we also plan to study the carbon-13 alpha N reaction at higher energies, because as I showed in a previous slide, there is still a lot of discrepancies among different data sets. And then we plan to study the neon-22 alpha N, which is the other neutron source for the S process. Just to give you an idea of where we stand at the moment for these reactions, as I mentioned, carbon-12, carbon-12, it's very difficult. There have been many studies over the years, but the situation is still rather messy. There was an indirect measurement published on Nature in 2018, which seems to indicate that there are lots of resonances in the gamma region, but no direct measurement has ever been done in this region. So clearly it will be very important to see what we can find. And then the carbon-13 alpha N I've already mentioned, and the other neutron source is here, and these is the kind of current status. There are measurements going back to 2001 as the latest to date, perhaps. and as you can see, nothing reaches the gamma region, and these values are just upper limits. So clearly there is still plenty to do in this lower energy region. Of course, this is what we plan to do at Luna, but Luna is no longer the only laboratory underground. There are others, and in particular the two at Homestake and Jinping in China, which really are also devoted to nuclear astrophysics studies. And just to give you a kind of comparison, this is where the other two laboratories are in terms of background reduction. So clearly we can expect significant results coming out from both of these laboratories. And indeed, I just saw yesterday that a first PRL has been published by our Chinese colleagues. So congratulations to you all for this major achievement. So as I said, in Homestake there is the American laboratory, CASPAR, Compact Accelerator Systems for Performing Astrophysics, and this is a collaboration between Notre Dame, Colorado School of Mines, and South Dakota School of Mines and Technology. And this laboratory was inaugurated in July 2017, and they've already started some measurements. And as I said, the Chinese laboratory, which already started operation already in 2020, and some results are already coming out. So very quickly, a final summary and outlook. Nuclear physics, as we have seen, really plays a central role in understanding of the universe. And the nuclear reactions are really important to show us how chemical elements can be produced and where, but also how stars are born, evolve, and die. And we have mentioned some of the key stages of stellar evolutions, but I'm sure you will hear many more in the course of this school from other lecturers. So nuclear astrophysics underground is a very fruitful area of research, and and this is the case because low energy nuclear astrophysics pose extreme challenges from an experimental point of view, so that doing measurements underground is really essential for major advances. I've shown you the pioneering work of Luna, which has led to major progress in various burning modes, hydrogen burning, CNO, neon sodium, magnesium aluminum cycles, and hopefully now new prospects are opening up to study also processes taking place during helium burning and carbon burning, and this latter specifically with the new Lunar Megavolt Accelerator. So clearly there are plenty of opportunities at Luna and elsewhere, as we have seen, and this hopefully leads to a bright future. So with this, I'd like to thank you all for your attention, and I look forward to seeing you all in our discussion sessions. Thank you very much, and of course, last but not least, a big thank you to the entire Luna collaboration.